to experience tonic current loop in uniform magnetic field. This was in the rectangular loop. This line is the axis of the loop. Part through which current can enter. Moves out of the loop to the other end. The axis is parallel to the length of the loop. PQ and RS represent the length. PQ equal to RS equal to L. Then QR equal to SP equal to D. That's a breadth of the frame. So that AD equal to length into length. It's a set of large number of turns of coil. Just for the explanation purpose only, it's on one coil. So SP is connected with large number of turns is one broken coil. So capital N stands for the number of turns. It will be the current passing through each turn. We have a magnetic field uniform. Magnetic field is acting from left to right. It's the magnetic field. Uniform magnetic field all around the pole. We just put three lines, one on the top intersecting with QR, one intersecting with SP, and the third one exactly in the midpoint of it. This is the third field line parallel to both. All the three are equidistant, representing uniform field. To get a 3D feeling, we are removing this part so that it's feeding, passing from the back and through the field. All current carrying conductors in magnetic field experience a force. We are finding force on PQ, QR, SP all. So force on PQ. It's equal to force on a current carrying conductor formula is I into L, length cross magnetic field. So L and B are vectors here. To open this up, will be I, current only, L is length here, PQ, B is B, then sine theta. Here if we check, length is PQ upward, magnetic field is towards right, so this angle theta will be 90 degrees, sine 90. Now, to find the direction of the force, L cross B. L is P2, which is J cap. Cross magnetic field is towards right, which is I cap. J cross I. I cross J is K, J cross I is minus K. So you get force on P2 as strength as I into L into B, sin 91, J plus I is minus K. Minus K means into the wave. The force will be acting into the wave. F1, P2. We find force on RS, the only difference is current is moving downward. So the formula for force on RS, everything is same, no difference. Only the direction becomes opposite. So it will be I, L, B, along plus K. You can see these two forces. One is acting into the screen and one is acting out of the screen. This will make the coil rotate about the axis. So the coil starts turning with RS coming out and P is going in, like this. This particular. The QR and SP force both act opposite and in the plane, up and down. So one force is upward and one force is downward, which is acting along the plane, not normal to the plane. So that will not produce any torque. So force on QR and SP are equal because the area, the length and magnetic field angle are same equal. Opposite, not only opposite, and act in the same plane of the coil. So it won't produce any torque, it won't rotate, just act up and down, try to displace, but they are getting cancelled. Hence, no torque. But you can see these two forces, PQ and RS, are equal, opposite, and acting perpendicular to the plane. So that only produced torque. Force on PQ and RS are equal, opposite, and act normal to the plane. Hence produces a torque. There are different ways of finding torque. Here you can find the torque as torque on PQ plus torque on RS. So torque formula is Rx sin theta. From the axis, the distance to PQ is B by 2, half of the QR. Again, the distance from axis to RS is B by 2. So Rx sin theta, R is B by 2. Then force is ILB. Then sin theta. Take sin phi and phi. Plus RS also, the length from the axis to that point is B by 2. Force is ILB. Then again sin phi, where phi is the angle between the area vector magnetic field. Phi angle between area vector and magnetic field. So here is the magnetic field. The area vector is always normal to the plane. This is the area vector. This angle is called phi. When you add these two, this will be 2 times b by 2 ILB sin phi is equal to b I first, ln b next. This will be replacing as area and capital B magnetic field side of that. So this will become finally I into ln B's area, AB side. There are m turns of the coil. Just multiply with m. So what will be equal to n times I AB sin phi. It's expression for the torque. You want to write in vector form, torque n I AB sin phi you can write as vector A cross vector B. A cross B is AB sin theta. So AB sin phi you can write as A cross B. So this is the final formula for torque on a current carrying coil in uniform magnetic field. Now, if theta is 90 degree, if theta is 90 degree, sin 90 will be 1 maximum. The torque will be just N I A, which is the maximum torque. For that, theta is 90 degree means area vector is be normal to magnetic field. This is the point. Current is flowing this particular way. The area vector will be out of the screen. If the magnetic field is towards the right. And this angle will be 90 degrees. That's the maximum point. Now, if theta is 0 or 180 degrees, theta 0 or theta 180 degrees. Now, sin 0 will be 0, so torque will be 0. Here, theta 0 means the area vector has to be parallel or anti-parallel to magnetic field. So this the diagram will be the coil is like this. the area vector will be like this towards right. Even the magnetic lines will be like this. That time area vector and magnetic poles are parallel. Theta is 0. So it will be 0. Even the area vector is opposite and magnetic field is towards the right. That time also it will be 0. So in that case, the coil same way. The area vector is to the right, the magnetic field is to the left. Theta is 180 degree, sin 180 is 0. So still torque will be 0. These are the two cases for maximum and minimum torque.